Okay, welcome to another episode of Pandemic Whiteboard in the Garage. Um, we talked about the fact that we still need to cover or discuss fluctuations, and that's, as promised, this is what this recording is going to be about. And so let's motivate this topic and let's quickly launch into it. We've been talking about the canonical ensemble, and in the canonical ensemble, the representative system that we are considering is in contact with the thermal reservoir. Our system has some number of particles, some volume, and some temperature. And the thermal reservoir is there to keep the temperature constant. And what we also talked about was that because the walls of this container of our system with a constant NV and T are diathermal, they're thermally conducting, that means energy can cross the boundaries of the box in the form of heat if the box is rigid with a fixed volume. And so the energy level that the system finds itself in at any given point in time is not fixed in time. We've talked about this before. It's a fluctuating variable. And so that's why we started talking about the average energy. The energy was viewed as a fluctuating variable, and there was some fluctuation to it. And the question now is, how large is this fluctuation? On average, what is the deviation away from the average value? And so this is the average, but any given measurement will give rise to some other energy value, whether below or above the average. And on average, how far apart are you from the average in a given measurement? For example, suppose the energy fluctuates a lot. And so imagine a scenario where if you were to measure the energy of the system as a function of time, you might find something like this. A system that fluctuates a lot. And maybe the average would be somewhere over here. Perhaps. Maybe this is the average. What that would tell us is that the average as a metric of this probability distribution, as a metric of this fluctuating variable, would not be sufficient to fully understand what your system is doing. Because the average value is certainly what it is, but at any given point, the fluctuation away from the average is quite large. And so it's not clear that the average is that useful of a quantity all by itself. Whereas on the other hand, if you had a system that fluctuated about its average value relatively little, then the average value effectively would be all you need to say. The fluctuations away from the average would be quite small. And so by stating the average value of the energy, you have more or less said what you need to say. Whereas here, just stating the average is not good enough. Yes, this is the average, but at any given point, the fluctuation away from the average may be quite large. And so one would want to also know, what about the size of the fluctuations, particularly the size of the fluctuations relative to the average value. For example, if the average energy is, 1,000 joules, and the fluctuation is 1 joule, then plus or minus 1 joule, then maybe that's not that big. But if the average energy is 1,000 joules and the fluctuation is 500 joules, then the energy is going to be wildly going up and down relative to the average. You will want to definitely know how large those fluctuations are to understand how the system energy is changing with time, where quoting the average value is no longer good enough, no longer descriptive enough as far as your system is concerned. And so we are in the business of understanding right now how large these fluctuations are on average for a macroscopic system that has about 10 to the 23rd particles and some large volume or macroscopic volume and some temperature. And so that's what we want to do. Now, how do we define fluctuation away from the average? And specifically, we want the average fluctuation away from the average. Any given one of these points, if this is the measurement of E, the fluctuation away from the average would be the instantaneous value of E measured at this point in time minus the average value. That's the deviation away from the average. This is some measurement at some time. This is the average value. The difference is the fluctuation away from the average, or the the motion of energy, or the measurement as it goes up and down relative to the average. We want the average value of this quantity. On average, not every fluctuation is the same. Here it's small. Here it's very small. Here it's very large. But on average, how large is the fluctuation? And so we would want an object that looks like this. The average value of the difference between the value of the energy and its average value. And so you can imagine finding the height of these fluctuations at every point in time, subtracting away the average value, so looking at just the height relative to the average value, and then averaging that, and so on. If you stare at this long enough, you can convince yourself that this quantity is 0. And the reason it's 0 is because if you wait long enough, on average, you will have just as many fluctuations going in the higher than the average direction as lower than the average direction, and they will average each other out. So averaged properly, the average should give you 0, because this quantity can be both positive and it can be negative. And so the negatives and the positives will, in the long time limit, average themselves out and average themselves to 0. And so by forming a quantity that looks like this, we can never fully get a sense for the magnitude of the fluctuation on average away from the average value. We need a mathematical quantity that is always positive, so that it doesn't average away with its negative to give you 0. And how do you make a quantity positive? You take its square. That's the simplest one. The square of a number is always positive. And so suppose we wanted to look at the square of this value. And so that's what I want to do next. Let me then erase this and just do it up above, and erase that as well. What we really want is this quantity, the energy minus the average value squared. This quantity can never be negative. And so even when this quantity is negative, this quantity will be positive. And this quantity will measure simply the magnitude, with no regard for up and down, the magnitude on average of the fluctuation. And so we need to average this, right? This is the value of the energy at some instantaneous measurement, or the value of the energy when the system happens to be in some specific microstate at some time. We want the ensemble average of this quantity, either a time average or the ensemble average. And we've made one of the postulates for us. One of the postulates was that the time average was equivalent with the ensemble average. And so using the Boltzmann probability distribution, we can calculate the ensemble average quantity, that is the square of the average deviation away from the average. We will ultimately then come and take the square root of this quantity. And that's going to be known as the root mean square deviation away from the average. And so we've given the symbol before, sigma. So let's write sigma sub e to remind us that this is the root mean square fluctuation away from the average in the energy, as square root average value energy minus the average energy squared. That's what we're averaging, and ultimately taking the square root of. Let's work with this quantity a little bit. I want to work with this quantity here. So specifically the averaging bracket quantity. So this. First, let us expand the square on the inside. This is going to be equal to averaging brackets. If we expand the square, we get the value of the energy in some measurement squared minus 2E times the average value of E plus the average value of E squared, whole thing averaged, ensemble averaged, or time averaged. The average of this difference, or this sum, some terms with a minus sign, some terms with a plus sign, is the sum of the averages. And you can convince yourself by doing some simple examples, because the averaging operation is effectively a summation itself. And so this is going to look like the average of the square of the energy, so the second moment of the energy probability distribution, minus average value of 2E times the average value, plus the average value of the average value, in a sense, squared. The average value of the average value doesn't make much sense. And that's because it doesn't really, you don't gain anything by averaging the average value, right? The average value is a constant. It's not a fluctuating variable, and so its average is the same thing. So this thing is just equal to the average, the square of the average value. The additional averaging brackets doing nothing additional. Here, similarly, the average value in this product is not really going to change. And so we're going to get the average squared minus the 2 can come outside, two factors of the average energy plus the average of the square. This is the square. Oops, you know what? I got my square wrong. The square is on the outside. This is going to be the same as that. So we get average squared minus twice square of the average plus the square of the average. That's what we get by doing this. And so if we combine this, if we subtract these two guys from that, what we arrive at is that the root mean square fluctuation is equal to the average of the square of the energy minus the square of the average. So this is the quantity with which we will now work going further. So in words, what we have to do is we have to use the probability distribution, if we're going to use the ensemble averaging, to find the square of the average energy. We then find the average energy and then square it after averaging, and then subtract this result from that, take the square root, that is going to be our root mean square fluctuation away from the average value. So let us work further with this. Notice, this is the second moment of the energy probability distribution. For us, that's the Boltzmann distribution. This is the first moment squared of the Boltzmann distribution. We know how to find them. We have set down rules how to calculate any moment of the probability distribution, and so let's do this. For this, we need to pull out the board for a second, hoping not to hit anything. Now we go back. I'll try to align myself reasonably well. Hopefully this is okay. Okay, so now we have to calculate two terms. First term we have to calculate looks like this. the second term we have to calculate looks like that. Let me remind you that the average square, or the average of the square, yeah, is 1 over q, q being the canonical partition function, sum on j, where j is the microstate index, e squared e to the minus beta e sub j squared e to the minus beta e sub j. The average value of the energy, we now know well, is 1 over q, sum on j, over all the microstates of the system, e sub j e to the minus beta e sub j. Remember, in our notation, by writing this as big E, that should remind you that we're talking about the system energy level, the many body energy level of the n particle system, not the single, not the, oops, something fell. Not the single molecule energy level. So that's where we are. So this is what I want to work with. Now, what I'm going to try to do is, this is the task that we have in front of us. Can we relate? We could write down what the fluctuation, average fluctuation away from the average looks like in terms of the square of the average and then the average value itself. And we could certainly write down what they look like in terms of the Boltzmann probability distribution. But can we arrive at a useful relationship that would perhaps give rise to a little bit of insight into what these fluctuations are physically related to? Is there some property of the system that determines the size of these fluctuations for different systems? And then also, how large do we expect these fluctuations to be for a macroscopic system? Those are the two questions that we'd like to answer. And so to do that, I'm going to ask you to look at something for a second and perhaps notice something. Notice that the only difference between these two expressions is the presence of this second power of the energy. This has the first power. How do you think one might go if you were to start with the energy expression having a single power in the sum to the second power? What mathematical relationship or operation might get you there? Well, you might notice that if you took a derivative of this function, you might find a way to bring down an extra power of the energy if you did the chain rule of the derivative. And then you would get the second power. And so what I want to do, and what we're going to do together, is we're going to ask that question effectively. Can we play a couple of mathematical tricks, no more than just taking a derivative, to see if the average energy can allow us to derive the equation for the square of the average, and in so doing, we hope to uncover some insight for those two questions. Questions being, is there something that differentiates the size of the average fluctuation for different chemical systems? Given two systems at a given temperature with a given volume and number of particles, if the systems were chemically different, how would the average size of the fluctuation change? And also, roughly speaking, for a macroscopic system, how large is that size of the fluctuation? So to do this, I'm going to rewrite this expression. I'm going to start working with this bottom guy. And I'm going to rewrite this expression by multiplying through by q on both sides. And so what this is going to look like is average energy multiplied by q equals sum on j. I'm going to omit the index now. E sub j e to the minus beta e sub j. And so what I'm going to do now is try to take this derivative. I will take a derivative with respect to temperature. And because I want to take a derivative with respect to temperature, I will have reason to write this in terms of temperature, right? So this is equal to sum on j e sub j e to the minus e sub j divided by kBt, having put in the definition of beta. And so that's what I want to do. I want to differentiate it with respect to temperature. So what I'm going to do is I'm going to take the derivative with respect to temperature on both sides. Trying to see, once again, that might look opaque why I'm doing this, but I'm trying to ask myself, if I were to differentiate this with respect to temperature, that would ultimately operate on this exponential factor, and it should bring down a power of energy in this expression. Sorry, it should be pointing to the average energy. And so that's the approach that we take. And so we take a derivative with respect to temperature on the left, which is product of E and Q, and on the right, d dt of the sum on J of E sub j e to the minus E sub j over kBt. That's what we're going to do. And for convenience, I'm going to call this the left-hand side, so I can operate or work with them separately and then put them together. This I'm going to call the right-hand side. So that's what we're going to do. I'm going to start with the left-hand side. And at this point, let me erase this and just keep on working there. Let me keep this separating line. So, working with the left-hand side, d dt of average energy times Q. Well, what is Q? Q is sum on J e to the minus E sub j over kBt. If I'm going to be differentiating this with respect to temperature, I'm seeing that I have a product of two functions. The first function is the average energy. The second function is the partition function. That's sum. And so let's apply the product rule. The first derivative that we get is this quantity, which should look a little bit familiar now. I'm going to write this just as Q plus the average energy times the derivative of the partition function. So let's find that. The derivative of the sum, remember the derivative is a linear operator, is the sum of the derivatives. And so this together once again equals times Q plus average energy. See how it should stand so you can see. Sum on J d dt of e to the minus E sub j over kBt. Now, when d dt operates on this factor, this is an exponential function with some inside function. Right? So this is the outside function is the exponential. The inside function is minus E sub j over kBt. And so there's going to be a chain rule that goes in here. When we take the derivative of the exponential, we get the exponential back. But then we take the derivative of the inside function. And so the result is, again, if we rewrite the first term, plus average energy. Now, sum on J, the exponential factor back. Oops, I shouldn't be writing beta. I should be writing this in terms of kBt to be consistent now. E sub j over kBt. Now times the derivative of the inside function, which is E sub j over kBt squared. Right, by taking a derivative of the inverse power of t You get multiply by -1, which cancels that minus, and then you bring down another power, so you get a t squared. So notice that we picked up a factor of e sub j in there. Okay. Now, that's the that's the right-hand side. But we can actually massage this just a little bit further. Let me just rewrite this as ddt times q. The kbt squared can come outside the sum. The e sub j has to stay inside the sum because e sub j depends on the index j, so it can't just come out. But kbt squared is a constant with respect to the summation index, and so it can come outside. And so this can also be written as plus the average energy divided by kbt squared times the sum on j of e sub j e to the minus, oops, again I try to write beta, e to the minus e sub j over kbt. Now I've done what I can with the left-hand side. I'm going to go back to the right-hand side. So this thing is the left-hand side, the derivative of this product. Now let me move on to the right-hand side, and for this I need to move the board out. Once again. We need to do a little bit of erasing. Okay. So now once again, I'm going to go work on the right-hand side. Then I'm going to put it all together and see whether I was able to extract any additional physical insight. And as I've said multiple times in this class, we wouldn't be bothering you if we didn't. So, the right-hand side from that derivative looks like ddt of the sum on j e to the minus e sub j over kbt times e sub j. That's the right-hand side. Now remember, the derivative operator operates on the sum and goes through the sum and operates on every term. E sub j is not a function of temperature. E sub j was one of the solutions to or one of the eigenvalues that resulted from the solution of the Schrodinger equation for our system. It does not depend on temperature. It is simply the Schrodinger equation eigenvalue for the system. What will depend on temperature is the Boltzmann factor. And so the energy value will be treated as a constant with respect to it. And so this looks like sum on j, e sub j gets left unharmed, the derivative operator operating on the Boltzmann factor inside. Again, I'm writing this as beta, muscle memory. kbt. And so this looks just like before. What is this going to yield? Oops. This is going to yield the exponential term back times the derivative of the inside function, which will be again e sub j divided by kbt squared. And so we get sum on j, e sub j, exponential factor back, now times again e sub j over kbt squared. This e sub j cannot come outside the sum, but the kbt squared term could. And so in fact, let's make this explicit. 1 over kbt squared, sum on j, e sub j squared times e to the minus, e to the minus E sub j over kBt. Notice that we got our second power of E sub j, which is what we mentioned might have happened. And so at this point, let us put everything together. The left-hand side gave us times Q plus average energy divided by kBt squared times sum on j E sub j e to the minus e to the minus E sub j over kBt. That was the left-hand side. Now equal to the right-hand side. Equals 1 over kBt squared, sum on j, E sub j squared, e to the minus E sub j over kBt. And so now let's do a little bit further massaging. First, what we're going to do is we're going to divide by Q. Why would we divide by Q? The reason we would divide by Q is Q would then end up in the denominator of both of these expressions. Notice that this is just missing a factor of 1 over Q to be the average energy. This is just missing a factor of 1 over Q to be the average energy squared, given that the probability is given by the Boltzmann distribution. And so by dividing by Q, we will be able to directly turn it into that. Let's go through the pain of actually doing this. And so we find an expression that looks like this. Since Q is a number, is a constant, it can go inside the sum as well, right? That's on the left. And on the right, we have sum on j, 1 over q, e sub j squared, e to the minus e sub j over kBt. And so now you can see that this is the average energy. This is the average of the square of the energy. And remember that the mean squared fluctuation away from the average value was the square of the average minus the average squared. But notice that this average is multiplying another factor of the average. So this is going to be the average squared. So now let me rewrite this up top. Erase this business with the right-hand side and write this up top. And so what this is going to look like is the average, or the derivative of the average energy with respect to temperature, plus the average energy squared over kBt squared. That's this factor multiplying that factor, equals 1 over kBt squared times the square, or the average of the square. That's what we find. Let's multiply by kBt squared and then also move this term to the right-hand side. If we do this, we find kBt squared on the outside. Let me rewrite this. kBT squared, the derivative of the average energy with respect to temperature, is equal to the square of the average energy minus this. Notice that the square root of this gives us the mean squared fluctuation. And so we can conclude then that the mean squared fluctuation around the average value is going to look like kBT squared. But what is the derivative of the average energy with respect to temperature? We've seen this by the terms of the heat capacity. In fact, the constant volume heat capacity. What was implied by our partial derivative was that the other variables on which the energy depends on were constant. So the number of particles and the volume were constant. And the derivative with respect to the energy with the volume held constant is the constant volume heat capacity. And so what we found, let me write this slightly differently so it's not a little crazy. What we found is that the average fluctuation away from the mean, the average root mean square fluctuation away from the mean, is square root of kBT squared times the constant volume heat capacity. It's kind of a remarkable relationship. Think about what this is saying. This is saying that I have a system whose energy is fluctuating because its heat can go in and out of the box. How large is the average fluctuation away from the mean, or the root mean square fluctuation away from the mean? It is related to the temperature, certainly. So the larger the temperature, the larger the deviation away from the mean. But also the heat capacity. That's not an expected thing. That's an unusual or a little bit of a difficult to anticipate result. That what determines the relative size of the fluctuation is the heat capacity of the system. And now we can answer in a sense the second question that we posed, or maybe it was the first, can't remember. But what distinguishes for a given temperature and a given number of particles and a given volume? What distinguishes the magnitude of the root mean square fluctuation away from the mean in the energy of one chemical system to another? And this says that that is determined by the heat capacity. So for example, if you were to look at water versus alcohol or water versus chloroform, they would have different constant volume heat capacities. And therefore, you will expect to get different magnitudes of the root mean fluctuation away from the average value. An unexpected connection that we wouldn't otherwise would have had trouble anticipating. And so the chemical nature of the macroscopic substance that you are interested in a sense, will dictate how large the root mean square fluctuation of the energy of the system you could expect. So that's the first question. That's the relationship. This is an important relationship. Now for the second question. What can we say roughly about the size of such fluctuations for macroscopic systems? And for macroscopic systems, we mean the number of particles is of order 1 mole, or roughly 10 to the 23rd, in that ballpark. The proper way to do this is to not look at the size of the average of the root mean square fluctuation by itself, but to look at its ratio relative to the average. Remember what we said at the beginning was that if your fluctuations on average are very large, the average value itself will not be an all-encompassing metric that describes the system energy. That if the fluctuations are large relative to the average value, then one would need to characterize also, higher moments of the distribution. And so the appropriate thing to check is the magnitude of the relative fluctuation, the root mean square fluctuation, compared to the average value of the energy. If this is large, but this is enormous, in a sense, the ratio will be, or not in a sense, the ratio will be small. And so compared to the average value in that case, the fluctuation should be ignorable. But if this is large and comparable to this, then the fluctuations could be of the same order of magnitude as the average itself. And that would be a wildly fluctuating function that goes way up and down by large, peaks and valleys relative to the average. In that sense, you can say the average is not good enough to understand the behavior, the time behavior of your system, the temporal behavior of your system. And so this is what I want to do. This quantity is first of all, let's note something. What we want to do right now is what's called an order of magnitude estimate. We're not going to care about small details. We're not going to care about factors of 2 or 3 or even 4. We just want the order of magnitude. Is this 1/2 of the energy? Is this 1/10 of the energy? Is this 1/100th of the average energy? What is this ratio? How large is the fluctuation relative to the average energy? Roughly speaking, what is the order of magnitude? And to do this, we need to get a sense for the order of magnitude of both of these quantities. Now, the average energy, where we can obtain the estimate for the order of magnitude of the average energy by thinking to our kind of tried and true system that we are fond of, that we're used to thinking about, and that's the ideal gas. The reason that is because from thermodynamics, from classical thermodynamics, we know that the internal energy of our system, and of course we've made the correspondence to the average energy, is approximately kBT when the temperature is T. Remember that for a monatomic ideal gas, it's 3/2. Or I'm sorry, not kBT, N kBT. Number of particles times kBT. It's kBT for a single particle. But for the whole gas, the average energy or the internal energy is approximately N kBT. Again, for a monatomic ideal gas, it's 3/2 N kBT. For a polyatomic gas, it's a different value, but still of the same order of magnitude as N kBT. The heat capacity is the derivative of the energy with respect to the temperature, and so it's approximately N kB, roughly speaking, without worrying about factors of 2 and so on. And so this provides us the order of magnitude. Why? The root mean square fluctuation is square root of kBT squared CV. So this is kB to the 1/2 T square root of the heat capacity. Square root of N, square root of kB. Divided by the order of magnitude estimate for the average energy, and that is N kBT. The T's cancel, the kB's cancel, and what you're left with is approximately, or actually not, let's keep this as, this was approximately 1 over N to the 1/2. So the relative size of the root mean square fluctuation away from the average relative to the average value of the energy goes like 1 over the number of particles to the 1/2 power. But for a macroscopic system, N, the number of particles, is roughly 10 to the 23rd. And so this quantity is roughly 1 over 10 to the 23rd divided by 2. What is that, 11.5? Something like that. an enormously small number. So the relative fluctuation in the energy of a system whose energy can fluctuate, the relative fluctuation compared to the average value for a system that has about a mole of particles is extremely small. The size of the fluctuation is basically negligible. So that we can now say that for a macroscopic system, if you were to plot the energy as a function of time, it would look something like this. You wouldn't expect wild fluctuations around the average. And so that's an important result. That we do, even though the energy can fluctuate, because the system has diathermal walls and it's in contact with a thermal reservoir, the relative size of the fluctuation in the average compared to the average value is minuscule. And so it's as if the energy didn't fluctuate. It's as if the energy was a constant value. And that's an effect because the system is macroscopic. If the system were not macroscopic, this quantity would not be small. How do we know? Let's see that explicitly. What I want to think about now is the size of the fluctuation in the energy, root mean square fluctuation in the energy, not for the whole system, but for a single molecule inside of our system, one of the n particles inside our system. What can we say then? So, system contains n molecules or particles. The average energy of the system as a whole, the average energy of the system is this. But the average energy of the system can also be written as in terms of the average energy of each particle. This should look like this. If each particle, on average, has this much energy, of any one particle or molecule, then the average energy of the whole system is just the average energy of a given particle times the number of particles you have. And so let's use this fact. Now, we're not going to go through the gory details, but what one can show is that the square of this quantity, the square of the average single molecule energy, the average of the square of the single molecule energy minus the square of the average single molecule energy looks like kBT squared, derivative with respect to the average single molecule energy with respect to temperature. Looks very similar when we were talking about the energy of the whole system. Now we're talking about the energy of average energy of a single molecule, and the square of the single molecule energy average is related also to the derivative of the single molecule energy with respect to temperature, just like we just saw a second ago. But this guy this derivative, yeah, I'm not showing you this. Let me just point out that you can look at Terrell Hill, page 66, to see that this comes about. This quantity is ddt So the derivative of the average single molecule energy with respect to temperature is d dt of average system energy divided by the number of particles, right? This is average system energy. But n is a constant, so this thing equals 1 over n d average energy dt. And we know what this is already. The derivative of the average system energy with respect to temperature is the constant volume heat capacity of the system. So this is CV divided by the number of particles, or the heat capacity per particle, in a sense. And so this quantity is equal to kBT squared CV over n. Remember that the average fluctuation in now the single molecule energy, sigma epsilon, is the square root of that quantity, right? It's the square root of this on the left, so it's the square root of that on the right. And so this looks like kb to the 1/2 t cv to the 1/2 divided by n to the 1/2. And remember that CV is still of the order nkb. Now let's do the same analysis as we did a second ago. Let us find the relative fluctuation in the single molecule energy relative to the single molecule energy itself on average. So we want sigma epsilon relative to the average value of the single particle energy. This is the single molecule average, single molecule energy, any one of the n molecules. This is the average fluctuation in the single particle energy. This quantity, its order of magnitude, as we saw before, is going to be kb to the 1/2 times t times cv to the 1/2. cv was of order what? Of order n kb. And so this is n to the 1/2 kb to the 1/2. Divided by what? Well, if the single particle, or if the system energy, roughly speaking, was n kBt, for the ideal gas is the estimate that we used. If the system energy was n kBt, the single particle energy, roughly speaking, was of order kBt. So this should look like kBt. Make sure I don't make any. Oops. Where did I make a mistake? I forgot. Right. So this was n to the 1/2, but this was also divided by n to the 1/2, which is something I forgot in the denominator. Right. So the n kb came from the order of magnitude estimate of CV. And because it's the square root of that, we have to take the square root of n and kb. But this thing was also divided by n to the 1/2. And so the n to the 1/2 cancels, the t cancels. Where am I? The kb's cancel. And so roughly speaking, the ratio is unity. The average fluctuation in the single particle energy away from the average value is the same order of magnitude as the average energy itself for the single molecule. Therefore, for the single molecule, if we were to plot the single molecule energy, you expect where perhaps this is the average single particle energy. And so for each molecule individually, its energy fluctuates a lot in the course of the time evolution of the system as it jumps from one microstate to the other. And so the single particle energy is crazy fluctuating. But the average energy of the system as a whole has a very, very small fluctuation in the energy. It's as if the crazy fluctuation of one particle is canceled out by the crazy fluctuation of the other particle, taken together. And so everybody's fluctuations for the single particles roughly cancel to give rise to a small net energy fluctuation for the system as a whole. Why is this important? Why are fluctuations important? Why is it significant that the energy can fluctuate for any given one molecule and do so quite a bit? For the chemist, the answer is because of chemical reactions. We know that to undergo a chemical reaction, one of the basic requirements is to have sufficient energy to overcome an activation barrier for a particular reaction. And so the speed with which, the rate with which you will acquire energy roughly approximately equal to the activation energy of a reaction will be determined by the size of the fluctuations. And so the magnitude of the fluctuation is significant as a metric for effectively the chance that you will acquire, a given molecule acquires enough energy and can overcome an activation barrier. And of course we saw that the average fluctuation, even for a single particle or the system, depends on the temperature. Right? So as we start heating our system up, we start seeing larger and larger fluctuations in the energy. And eventually, some molecules begin to make it over the activation barrier and react, roughly speaking. And so that's what we wanted to say about fluctuations. This is the end of it, and I hope you now have added to your toolkit of how you should be thinking about a system in contact with a thermal reservoir as all of its particles are fluctuating among its possible energy levels, yet giving rise to a very small average fluctuation away from the average value of the energy for the system as a whole if the system is macroscopic.